Two topics for this video. We're going to talk about subgraphs and we're going to talk about isomorphism. So let's just jump right in. For sets, we had a notion of a subset, and for graphs, we're going to have a notion of a subgraph. And in fact, the definition of a subgraph is going to piggyback off the definition of a subset, which makes sense because our graph is just a pair of sets. So if I have a graph G and a graph H, then we're going to say that G is a subgraph of H. Well, if its vertex set is a subset of the vertices, so VG is a subset of VH, and the edge set is a subset of the edge set of the other graph. So again, that's now EG is a subgraph of EH. Okay, these are the two conditions of these two conditions. All right, so pretty simple. If we have these two conditions, if G is a subgraph of H, then we are going to write, already messed it up. We're going to write G is a subgraph of H, and we'll use the same subset notation. So it makes a lot of sense that pairs of sets correspond to, pairs of inclusions gives us this inclusion, this subset. We can write it out if you like, because G is VG, V8, is VG, EG, and H is VH, EH. All right, so we got the two sets, and that's it. This is what it means to be a subgraph, and that would be the whole story. It would be pretty simple, but it's going to get a little bit more complicated, just because we might find that this notion of subgraph, which will be our formal definition of a subgraph, is a little bit restrictive. And it's restrictive in that it doesn't always allow us to express directly some of the intuitive notions that we see all the time in graphs. So, but before we get into the complications, let's do at least one example where we do have a subgraph and one example where it's not a subgraph. Okay, so here is an example. The graph P3 is a subgraph of K5. Okay, so I've drawn K5 here, and if I'm going to find this subgraph P3, in pictures you can just see it. You see like, yeah, here it is. Here's that path of length 3. I go 0 to 1 to 2 to 3. Right, remember P3 is the path with 3 edges. 3 edges. So let's see if this marker works better than my other one. In this case, we can just check that these two conditions are met. Even though we sort of see it in here, we have a formal definition, which is written in terms of sets, and so we can check that those sets are indeed subsets, and so that this formal definition is satisfied. So the vertex set of P3, by definition, is the numbers, actually it goes up to 4, right? So it's 0, 1, 2, 3. How's that look? Oh, that's a nice 4, huh? These are our vertices. Let's get rid of that. Let's see, check my bin of markers here. I think my blue is working pretty well. All right, so there's the vertex set of the path, which of course is a subset of if I took the numbers from 0 to 4, which is the vertex set of K5. All right, so I have that the vertex set of P3 is a subset of the vertex set of K5. That was condition 1. Check that off. Now we have to check about the edge set. A little bit more work here, but not so bad. Right, the edge set of P3, we can write it out explicitly. We know there's exactly 3 edges. It's the edges 0, 1, 1, 2, and 2, 3, which is certainly a subset of all pairs of numbers from 0 to 3. So we write that, remember, as the set, this range, 0, 1, 2, 3, choose 2, which would be a subset if we took a larger set here, 5, which is the edge set of K5. Remember, by definition, it has all pairs of edges. So again, we've got now edges of P3 are all in the edge set of K5. So this is also a subset. And so we have this subgraph relationship. Okay, this one, pretty easy. And let's just check an example where they're not subsets. So in this case, I've got S3. Let's draw a picture of it. That looks like this. It's got three spokes, if you will, 3 points on this star, and we numbered them 0, 1, 2, 3. And then we have another graph, P3, which also has vertices 0, 1, 2, 3. And it also has 3 edges. So we have 3 vertices, 3 edges, or sorry, 4 vertices, 3 edges, but they're not isomorphic because, well, the vertex set of S3, this is in fact the case that they have the same vertex set. In both cases, it's these 4 vertex sets. I guess it's redundant to write it twice, but these are equal. And now for the edge set, I claim that the edge set of S3 is not contained in the edge set of P3. And if I want to show that one set is not a subset of another, it suffices for me to find at least just one thing that's in here that's not in here. So I just observe that there's this edge. In fact, are there any edges? I guess they have only one edge that really is in common, this 2, 3 edge. But let's pick, say, this one as our counterexample. 0, 3 is in the edge set of S3, but not in the edge set of P3. And so that suffices to show that this subset relationship doesn't hold, and therefore this subgraph relationship doesn't hold. So these are not this S3 is not a subgraph of P3. Again, these very small examples, it's easy to just look at a picture and kind of feel like, oh, I don't see this graph inside here. Or I can just look at the map the vertices according to their numbers and see if they look the same. But the point is not to be able to just work on these very tiny examples, but to have definitions so that you can really say what's true no matter what the graph looks like, no matter how big it is. All right. In many cases, we get a subgraph by actually taking stuff away from a graph that we started with. So if you start with some graph, let's call it H, and you remove edges, you leave all the vertices, but you remove edges, then that's going to be called a spanning subgraph, right? So this is this means that the vertex set of G is actually equal to the vertex set of H. Now it also has to be a subgraph, so I'll just remind you, because it has to be a subgraph, it means that the edge set has to be a subset of the edges. Right, so I possibly remove some. It could have removed 0, it would still be a spanning subgraph. But the key feature of a spanning subgraph, the spanning feature, is that all of the vertices in H also appear in G. Right, so if I just remove edges, I get a spanning subgraph. If, on the other hand, I remove vertices, this is a little bit more complicated. I have to put a little asterisk here. Asterisk, I'll say that, enunciate it clearly. Because if I remove vertices, I've got to also remove any incident edges, because I want it to still be a graph. If I just removed vertices, but there were some edges incident to it, it wouldn't satisfy the definition of a graph, because I might end up with some edges that were not pairs of vertices, because the vertices are gone. Okay, so this is a little bit more complicated operation, but the definition is also still pretty simple. It just says that the edge set of G is just equal to whatever the edge set of H was intersected with things which are pairs of vertices in G. So this is just a set theory way of describing the fact that you kept all of the edges that you could given which vertices you took. Right? So again, this also has to be, the vertex set of G has to be a subset of the vertex set of H. Just remember to put that in here. VG is a subset of VH. So it is a subgraph, but it has this key property. So again, if it has all the possible edges among the ones among the vertices that you kept, then it's an induced subgraph. So let me draw a quick example of this. If I have the graph that looks like this, if I take away a vertex, let's say I look at only the vertex set on these three, then the edges, I have to keep all the edges between those. And I throw out just this one vertex here and the two incident edges. Okay, that gives us an induced subgraph. And when you think about constructing subgraphs by removing stuff, it becomes a more active process. You almost think of it like an operation that you did on graph, like you're doing this kind of like, I almost want to call it a surgery, but surgery, I guess you're putting stuff together. Here we're just tearing stuff apart. If I have a subset of edges, you could think of this now as an operation on the graph H, which is going to give me a new graph, right? I can think of it as taking H and removing the edges E. And we're going to write that like this, H minus X. So we're going to use this set minus notation and sort of an abuse, but we'll have to know what type of thing this is here to know what we mean. But if it's a set of edges, then we're going to get a new graph which has the same vertex set as before, and it just takes the edge set minus X. Similarly, if we have some subset of vertices of H, then if we take H minus that vertex set, what we mean is, well, we're going to have whatever the old vertices minus S, and then the edge set will be exactly what it needs to be the induced subgraph. So we take everything, sorry about that, it's going to be everything in H that's still spanned by vertices that we kept. So this is VH minus S, choose 2. So this is the kind of perspective where we think about which vertices we removed. But on the other hand, you can also imagine saying like what vertices we kept. So if instead I have some other subset of vertices of VH, I could think about the vertices that I kept and I get another subgraph there. Let's call it H square brackets T. This is going to be the induced subgraph where I just kept the vertices T. So T that's the vertices I've kept, and the edges are anything in T choose 2 that was also in the original graph H. Okay, so this is constructing subgraphs or specific kinds of subgraphs. Obviously, you can end up with subgraphs which are neither spanning nor induced. But if you build a subgraph by just removing edges, you get a spanning subgraph. If you get a subgraph by just removing vertices and only those edges incident to the vertices you removed, you get an induced subgraph. And here's the kind of formal definition. And now, once you have these two, again, you get these kind of operations on graphs, like removing edges. You can write it in this set minus notation. Removing vertices, we use the same notation, so you kind of have to know what type of thing S is, in this case, to know if you're removing vertices or edges. But then there's this complementary view of thinking not about what you removed, but what you kept. And this is the induced subgraph on T. And so these two operations will always give you an induced subgraph. This operation will always give you a spanning subgraph. All right, so this is all pretty good. We got subgraphs. We've got some special kinds of subgraphs now. But here is where things get a little annoying. Like maybe the definition isn't so satisfying when we see this. So let me draw these graphs. Right, S3 and S4 are going to be our stars on 3 and 4 edges. Right, so here's S3. Right, it has vertices 0, 1, 2, 3. And here's S4 over here. Looks very similar. It has vertices 0, 1, 2, 3, 4. Okay, so is this a subgraph? Should we write this as a subgraph? It seems like, actually, according to our definition, the answer is no. But if you look at it, it feels like it should be a subgraph. You look at it, you say, there it is. Like, I can just see how they should, this graph just kind of sits inside this other graph so perfectly. In fact, when I was drawing it, I started with a drawing of S3, and then I just added another edge to get to S4. In fact, it doesn't just feel like it should be any old subgraph. It even feels like it should be an induced subgraph, because if I just take the vertices, vertices 0, 1, 2, and 4, and I take the induced subgraph, I get like the same picture. But it's not the same graph according to our kind of the definition we have. So when you look at this example, it's easy to start to think that maybe the definition is wrong. And in math, you can do this thing which sounds terrible, which is that I would like it to be true. I would like to say that this is a subgraph, but it doesn't fit the definition, so I'm just going to change the definitions. I'm just going to rework my definitions to make it true. Doesn't that sound terrible? But on the other hand, this is actually the normal way to do math, and it's actually how you discover more interesting and nuanced definitions. So we're not actually going to change what it means to be a subset. We're going to try to figure out in what sense is this really a subgraph. And that's where we're going to get to this, this question, like when are two graphs really equal? Because right now we've only had an intuitive notion that we borrowed from set theory. Really, we've been saying that the graphs are equal if, well, as pairs of sets, each element in the pairs should be equal. So G and H should be equal as graphs if the vertex sets are equal and the edge sets are equal. And we know what equal for sets mean. And that's reasonable. It's the right definition, but it gets us in trouble when we try to do really simple things like saying that, this thing right here, this graph that I've just drawn, well, that's a path on two edges. It feels like you should say that's a path on two edges. That's P2. But P2 is this other set, this other graph on this other vertex set, 0, 1, 2, and you say, oh, come on, they're the same. Right? You should just say that these are the same. And so what we need is a definition that explains really what we mean by sameness here, because this is really equality, and then we get it from set theory. It has a good firm foundation. The equals here is going to be a different kind of equality. It's what we call isomorphism. So we're going to say that G is isomorphic to H if there's some way to kind of map G into H. So let's give this one name. Let's say this was G and this was H. And that mapping is going to happen by mapping vertices in G to vertices in H. So there has to exist some kind of mapping, and that mapping should be a bijection. So it has to be this bijection. Let's call it F, mapping the vertices in G to the vertices in H, such that, such that now once I map the vertices over, they should have exactly the same edges. So if there's an edge over here, it should be an edge over here. If there's an edge over here, if I kind of took the inverse of this bijection, I would find an edge over here. So that is the same as saying that any UV is an edge in G if and only if f of u, f of v is in the edge set of H. And when we see this, we're going to write this as, G is isomorphic to H. So we're going to use that same equal sign with the tilde on top to refer to isomorphism the same way we did for sets. And in this case, we can just check that it really is true. We can write down what that bijection should be. So let me write it here. Let's say, do the obvious one, which is that ABC should map to 0, 1, 2. And I'll write this like this. ABC maps to 0, 1, 2. Okay, and by this, of course, I mean that A maps to 0, B maps to 1, and C maps to 2. Okay, and this is clearly a bijection. It's now up to us to check that this main condition of this bijection, that it maps edges to edges and non-edges to non-edges, is satisfied by this one. So let's just check. Right, I've got edges A, B, right, maps to 0, 1, right? So this is an edge in G, this is an edge in H, good to go. I have the edge BC in G, maps to the edge 1, 2 in H, and that's also present. And now I also have to check that the edge that's not here, right, that AC maps to 0, 2. So AC was not an edge here, it should not be an edge here, and that is true. Right, so we've checked all possible pairs in G to see that if it's an edge, it maps to an edge, and if it's not an edge, it maps to something that's not an edge in the other graph. And so we see that, in fact, just by manually checking, we check that this really is an isomorphism. Now, this definition is okay. This is the one you'll find in most textbooks. You'll find it on the internet. There's another slightly more advanced definition, let's say, that's actually simpler when you understand how it relates to our isomorphism of sets and other kinds of isomorphisms. And we'll get to that next time. But for now, let's just check now that this statement about S3 and S4, we can at least express it as a statement about isomorphism. So S3 is not a subgraph of S4, but it's at least isomorphic to a subgraph of S4. So let's just pick one. Let's take like this subgraph here. All right, so here is a subgraph of S4, and the claim now is that this S3 is isomorphic to a subgraph of S4. And again, if you just look at the picture, you know it's true, but you want to also show that it's true according to the formal definitions. So in this case, I can write down this isomorphism arithmetically. I choose this subgraph because I can just write f of I is equal to I plus 1. And so that means that f is going to map, f maps 0, 1, 2, 3 to 1, 2, 3, 4. Okay, this is clearly a bijection. In fact, I can even check that it's a bijection by writing the inverse, which is f inverse of I is equal to I minus 1. And I have a bunch of edges to check. I'd have to check, I guess there's 6 different cases to check. Let's just do it by hand here. I won't write them all down. Every edge in S3 is of the form I comma 3. So we have I comma 3 maps to, should be f of I, f of 3, which is I plus 1, 4. Okay, and every edge of the form something 4 for 0 up to 3 is in S4. So we definitely have all the edges in S3 are contained in the edges of S4. So that's, sorry, the image of them, right? So this is the edges of S3 get mapped by F in some sense. I'm going to draw this as a wiggly line because we haven't really made this clear what it means to be mapped by F, but get mapped right into the edges of S4. And now we also have to check that if there's an edge over here in this subgraph, this isomorphic subgraph, that it's also present here. And that's also not so hard to check. We could just check that 1, 4 is here. In fact, we could have just checked that this mapping here is surjective, and therefore we know it's injective because F is injective, and it's also surjective, so it in some sense gives us a bijection on the edges. Now, later we'll try to talk more clearly about how a mapping on vertices gives us a clear mapping on edges in cases where it's not even a bijection. But for now, let's just make some observations. One is that this thing is not unique. And there's two different ways in which it's not unique, right? It's not the only subgraph. So we could have picked, actually, I think 4 different subgraphs that are isomorphic to S3. And once you pick a subgraph, it's not the only isomorphism. That is, if you think of this f, right, this function on the vertices as the isomorphism, it's the map that does the equivalence, I could have chosen a bunch of different ones. So sometimes there's choices here. When we have this, though, as long as it exists, we will say that S3 is isomorphic to a subgraph of S4, but that's a lot of words to say. Oftentimes you will hear this. I will try to be careful, but I'll probably say it too. We'll often say that G is a subgraph of H when we mean really that there exists some, let's call it G prime, such that G is isomorphic to G prime, which is the subgraph of H, right? So it's isomorphic to some subgraph. And sometimes we won't make this distinction. Hopefully, like I said, hopefully we'll be careful about it. If I say something like if it has a subgraph isomorphic to G, or if it has a G subgraph, then usually I mean that it at least has a subgraph isomorphic to G. Right. And so that gives us our way of talking about subgraphs, at least up to isomorphism. Now we'll talk more about how to think about isomorphism in terms of other important graph properties. In fact, isomorphism is going to be at the heart of every graph property that we study, because if you have a property of a graph that's interesting to you, it seems like it shouldn't matter what the names of the vertices are. And that's turns out to be literally true for just about every graph property we study. So if you've got something that's true about your graph and another graph is isomorphic to it, then it should be true about your isomorphic graph as well. So we'll get into that next time.